As we have established, air has mass, and since it has mass, it will possess kinetic energy when in motion. Air in motion will exert a force per square meter on any object in its path. The formula for kinetic energy is half the mass times the square of the speed. This force per unit area is called dynamic pressure, because the air is moving in relation to the object being considered, in this case an aircraft. The dynamic pressure is proportional to the density of the air and the square of the speed of the air flowing over the aircraft, and is denoted by the symbol Q, in either upper or lower case. An aircraft in a moving airflow will therefore experience both static and dynamic pressure, as static pressure is always present. Let us consider the kinetic energy of 1 cubic meter of air moving at a stated speed. It is the product of the local air density, ρ, and the square of the speed in meters per second, divided by 2. If this cubic meter of air is completely trapped and brought to rest by an open-ended tube, the total energy will remain constant, but by virtue of being brought completely to rest, the kinetic energy is converted to pressure energy. This pressure energy is, for practical purposes, equal to half the density times the square of the speed, usually referred to as half ρv squared newtons per square meter. Let us consider an airflow of 100 knots, which is 52 meters per second, at ISA density of 1.225 kilos per cubic meter. Dynamic pressure is half ρv squared. That is 0.5 times 1.225 times 52 times 52, which equals 1,656 newtons per square meter, or 16.56 hectopascals. If the speed is doubled, dynamic pressure will be 4 times greater, as the factor in the equation is speed squared. Half times 1.225 times 104 times 104 equals 6,625 newtons per square meter, or 66.25 hectopascals. In a tube of an area of 1 square meter, a force of half ρv squared newtons will be generated. Regardless of the actual numbers involved in this example, it is important to remember the proportions. If speed is doubled, the pressure is quadrupled. If speed is trebled, the pressure increases by 9 times, and so on. If speed is halved, pressure reduces to a quarter of its previous value. Dynamic pressure is common to all aerodynamic forces, and determines the air loads imposed on an aeroplane moving through the air. It is well worth remembering a few key facts about dynamic pressure. A pilot needs to know how much dynamic pressure is being generated, but it cannot be measured on its own, as static pressure is always present. In this context, the sum of the two pressures is known as total pressure. Other terms for total pressure are stagnation, or more usually, pitot pressure. The equation total pressure equals static pressure plus dynamic pressure can be rearranged to show that dynamic pressure equals total pressure minus static pressure. The significance of dynamic pressure in understanding the principles of flight cannot be overemphasized. Because dynamic pressure is dependent on air density and aircraft speed, you need to appreciate fully the factors which affect air density. So, to reiterate the points covered earlier in the lesson, increasing temperature decreases air density. Decreasing static pressure decreases air density. Increasing humidity decreases air density. The reason for this is that water vapour is about 5/8 the density of dry air. Humidity is most significant for takeoff and landing performance, but is actually not factored when considering aircraft performance. Increasing altitude will decrease density, because the effect of decreasing pressure is more dominant than that of decreasing temperature. All aerodynamic forces acting on an aircraft are determined by dynamic pressure, so it is essential to have a way of measuring it and presenting the information to the pilot in the required manner. A sealed tube, open at the forward end, is located to face into the airflow created when the aircraft is moving. The pressure in the tube, which is known as the pitot tube after its inventor, 18th century French hydraulic engineer Henri Pitot, is dynamic plus static, and in this context is called pitot pressure. A way of subtracting the static pressure from the total has to be found, and this is achieved by way of one or more vents located on a surface parallel to the airflow, usually on the fuselage, which will sense static pressure. If you look at the diagram on the screen, you will see that pressure from the pitot tube is fed to one side of a diaphragm inside a sealed case, and static pressure to the other. The two static pressures, essentially the same pressure, cancel each other out, and the diaphragm will sense only dynamic pressure. Movement of the diaphragm moves a pointer over a scale, so that the changes in dynamic pressure caused by changes in airspeed can be observed by the flight crew. But the instrument is calibrated to ISA sea level density, so will only give a true indication of airspeed when the density is 1.225 kilos per cubic meter. At any constant density, the faster the aircraft moves through the air, the greater will be the dynamic pressure. This isn't a problem, since the pilot needs an indication of dynamic pressure, which is what the instrument, the airspeed indicator or ASI provides, being made in such a way that it indicates the square root of the dynamic pressure in nautical miles per hour, known as knots, or in some old aircraft, in statute miles per hour. So if this indicated airspeed is doubled, the speed of the aircraft through the air will also have doubled. There are, perhaps rather confusingly until you are familiar with them, several different categories of airspeed. The simplest is the indicated airspeed, IAS, which, as its name implies, is the airspeed shown on the ASI. Calibrated airspeed is an accurate measurement of the dynamic pressure of significance when the aircraft is flying slowly. The position of the pitot tube and static vents, and the aircraft's undercarriage and flap position, or configuration and attitude, will all affect the pressures that are sensed, particularly those at the static vents. Under these conditions, a false dynamic pressure will be sensed, resulting in a false IAS display. When IAS is corrected for this error, which is known as position or pressure error, the resultant speed is calibrated airspeed, CAS. The error may be placarded in the cockpit or in the flight manual, and will include known instrument error. Equivalent airspeed, or EAS, is the corrected airspeed achieved by allowing for the compressibility of air at high speed, usually only significant above 300 knots. Air is compressed in the pitot tube, giving a false, higher IAS. At a given density, the amount of compression depends on the speed of the aircraft. EAS allows for both position and compressibility errors. True airspeed is the actual speed of the aircraft through the air. and is the only real speed of those considered so far, all the others being dynamic pressures. The ASI is merely a pressure gauge calibrated to read as speed. TAS is EAS divided by the square root of the relative density. That is the ambient density as a proportion of the ISA sea level density. The ASI is calibrated to ISA sea level, so it will only read TAS if the density is 1.225. Thus, at 40,000 feet, where the density is close to 1/4 of the sea level value, the aircraft will be moving through the air twice as fast as at sea level to maintain the same EAS. The speed of sound, which is symbolized by a lowercase a, varies with temperature. Sound waves are weak pressure waves, which propagate from their source spherically through the atmosphere. The speed at which these sound waves travel is proportional to the square root of the absolute temperature of the air. The lower the temperature, the lower the speed of sound. On a standard day at sea level, the speed of sound is about 660 knots, or 340 meters per second. At high true air speeds and/or high altitudes, it is essential for the pilot to know his speed relative to the local speed of sound. This relationship is called the Mach number, symbolized by a capital M. The formula for Mach number is TAS divided by A, the local speed of sound. For example, if the aircraft's TAS is 4/10 of the speed at which sound pressure waves propagate through the air around the aircraft, the Mach meter will register Mach 0.4. How the Mach meter works is covered in the instruments syllabus. If an aircraft's speed approaches the speed of sound, there will be a Mach number at which the speed of the airflow over some parts of the airframe, usually the point of maximum thickness of the aerofoil, first reaches the speed of sound. This Mach number is called the critical Mach number, or M-crit. Certain operating or limiting speeds that are significant in the operation of an aeroplane are given abbreviations for easy reference, known collectively as V-speeds. There are many of them covering the entire flight envelope. For example, VS, stalling speed, VR, rotate speed, and VY, best rate of climb speed. All the above-mentioned speeds are calibrated airspeeds, as they relate to operations at low speed. Maximum operating, VMO, is an equivalent airspeed because it is a high speed. However, all the speeds quoted in the flight manual are adjusted to indicated airspeeds, since this is what the pilot will see on his ASI, which may have coloured arcs around the outer edge to indicate some of the main limit speeds. The atmosphere is the element in which aircraft operate, and it is important that you understand how the properties of the air, pressure, temperature and density change throughout the part of the atmosphere in which you fly. It is particularly important that you understand the concept of dynamic pressure and how it is involved in many of the aspects of the principles of flight. The next lesson deals with basic aerodynamic theory, in which you will see the application of some of the facts you have just learned.